Alright, another DraftScience video presentation. So apparently, this conversation, okay, with people who are interested in the subjects of how's the mechanical universe work, what's the truth, blah blah blah. You assume anyway. It has more than one phase to it in a sense. More than one. There's more than one difficulty in puzzle creation, completing this puzzle. It's not only, okay, that you have to find the right colors and the right piece shapes, and you have to be clever enough to, figure out, the missing bits and be able to still make the puzzle fit together. Once you've done that, you have to go through this arduous process of explaining why this is correct. I mean, even though the image is perfect, and everything fits, you have to explain, you have to prove it in some way. Somehow you have to prove that all other combinations of the pieces or something wouldn't make any sense. It doesn't work. And you have to go through this whole process of convincing, even though the completion of the task should have been enough. Even though you have a videotape of the putting the pieces together. It's a very strange impediment. It's like it's a difficult task, like brain surgery, and then they require you to do it blindfolded, and you're just like, well, what's this standard for? So I would argue that the fact is there have been other people before me who drew exactly the same conclusion I did. Okay, that this formula doesn't make any sense, and they wrote papers trying to explain why it doesn't make any sense, and they were entirely ignored and nothing advanced, and there was just nothing accomplished. And so I'm sitting here saying, well, I've got to somehow do that same thing differently, or in such a way as you understand that it is understood. So I guess I would first say that yes, the other papers lacked proper analogy, proper emphasis on just how dramatic this mistake is, how important it is, and so I have done more of that, but it hasn't been effective. It hasn't worked. So I did find this paper a while back. I've been reading it. It's 130 pages worth of 140. Going over the history of the controversy, and it's just so funny because they dismissed the controversy in the beginning of the article. So I'll read the couple of paragraphs here, and at the end dismiss it. It's just semantics. And it's, that's hilarious, right? Because in any other circumstance, this wouldn't be called semantics. It wouldn't be semantics if the IRS told you owed $1 million in tax instead of $1 in tax. No one would call that semantics, So in no other field, like in biology, if somebody had a theory, that the human genome was an invasive bit of code, from outer space, and space humans different. I mean, it would be a dramatic departure in the entire science of genetics. It would provide so many inconsistencies and incongruities. It would just completely break the current knowledge of how genes function and how it's possible to understand their function over time, and the evolution really only goes one way, and lots of theory would just be blown out of the water. And that's how dramatic this is. It's an incredibly dramatic controversy in the sense of difference. I mean, doubling, tripling, quadrupling, even more insane examples of the bullet versus the bowling ball, where you have 100, the bullet has 1,000 times perhaps more energy, as understood as a word, than the bowling ball. Dramatic implications. And then you get into the whole nuclear theory. If they're going to use this mechanics, it's an understanding of how the universe works. It's a description of the reality where the two descriptions are completely different in terms of how much energy an electron has, or a proton has, or an atom has. Extraordinary differences. So this is, it's almost mockable that the science historians, as they call themselves, are this clueless. that they really don't understand how completely opposed these two theories are. It's wave particle. I mean, it's an insane, amount of difference, and they're just saying, well, we can live with that. No big deal. Yeah. And again, in no other field would it be tolerated, because in no other field could you explain away how much it breaks the science. And in physics, you can get away with it because the science is so broken anyway. It's such a pile of crap that you can't see that it's completely broken by some kind of logic that can't possibly make any sense. The two universes created are so fundamentally different. There's no compatibility. There's no whatever they use. Nothing complementary in their usability. They describe two completely different universes. All right, so I guess I'll read the paragraph first, and then I'll go into trying to explain, which all I can do is reason with you, how people's perceptions are just clearly, they just don't see the universe the way it should be seen, and how we know it's got to be. But anyway, all right, so the publication of Leibniz's article marks the beginning of the vis-a-vis controversy. So his article was an attack against Newton's physics and Descartes, and this whole quality of motion, the idea of what drove the universe, and again, the equation wasn't even the current kinetic energy equation; it was just mv squared. So we know it was at least 100% wrong. And the real point is it's thousands of percent wrong. The faster you get something going, the more and more energy it derives from the same exact impulse. So the same impulse somehow makes lighter things have so much more capacity to change the universe than the heavier things, which is completely anti-Newton. It breaks all of the celestial dynamics. None of it could make any sense anymore. All of Newton's logic is gone. It doesn't work. I mean, it's just a plain fact that it will not work if you try to use this energy formula to decide, how much of an impact is going to move, say, a planet, or is going to change the course of an asteroid. It can't possibly work. So anyway, where was I? Mark the beginning. Okay. A dispute which occupied the attention of most European natural philosophers. So they, again, using this term that's just so ew, for about 50 years. Scientists, you could just say, scientists found it an interesting controversy. By and large, affiliations in the dispute went by nationalities, with English Newtonians and French Cartesians following the old opinion, that force is proportional mass times velocity, while Dutch, German, and Italian scientists favored the new opinion put forward by Leibniz. Now, eventually, like page 137, this guy gets to the core of it, which is really just about realizing whether you're going to understand a force based on how long you're in the force, the time, or the distance you travel in the force. Which one is the significant event? The time you're in it, or the distance you travel through it? And Leibniz are the distance people. They're going by how far does it go, and that's everything. And the other side is more about how long was it in the force? How much exposure did it get to either the opposing force or the impulse force? And the more time you're in the force, the more force you're going to collect. All right. And that was really the controversy. Okay. So the vis-a-vis controversy has always been something of a puzzle to historians of science. So apparently the historians of science think it's puzzling that there'd be any controversy at all. Like somehow, why didn't they see the automatic compatibility of completely different descriptions of a quantity? So you have a quantity, it's called energy, the capacity to move molecular bodies. You know, and it's okay if we, say 2 plus 2 equals 490, or we say 2 plus 2 equals 4. We know one of the answers is right? So either we say 2 plus 2 equals 1, or we say 2 plus 2 equals 968, if you want to look at it from that direction. You're just saying, which one is, come on, which one's got a hope of being correct? Anyway. Okay, puzzle to historians of science. In his short textbook, A History of Physics, Florian Conjuri calls it a curious dispute. He accounts for the episode by endorsing the view expressed by D'Amelette in 1743, so this is about when the controversy was dying, that this is a dispute of words, too undignified to occupy the philosophers any longer. So again, they're getting dramatically different descriptions of something's energy. Not small, like, oh yeah, 0.00007% off. I mean, these are, if these were error factors, they're gigantic. I mean, humongous. Just without a doubt, just insanely big. Yeah. And here they're pretending, well, there was nothing to really argue about. And so right here, you're just saying, how insane are these people, right? I can't call this anything else but insane. To say there wasn't anything worth arguing over when you're getting fundamental, I mean, the difference is an electron has, 10 million joules of energy, or it has 150. I mean, these differences are gigantic, not, piddle paddle, fiddle faddle, fooey dooey, who cares? I don't know. I don't know what to say. So anyway, so most traditional historians of science have agreed with Conjuri's judgment. This is, they have maintained that the expression force of a body in motion was ambiguous. I don't know, that's ambiguous? You're basically just saying, what does it contain? What is the force in there? What's the change that it has, that it will impose on the universe? There's nothing ambiguous about that. All right. In that it is used by the participants in the vis-a-vis controversy to stand for two completely different quantities. They're not different quantities, so this is just insane to say. It's only the same exact variables for both formulas. I mean, all you have is mass and velocity, and they're hugely disproportional statements about how important they are. Hugely disproportional. 1/2 mv squared. Huge disproportion. Okay. Controversy to stand for two completely different quantities, one of which was proportional to mass times velocity, while the other was proportional to... They weren't even proportional. They're explicit statements, essentially. This isn't a proportionality. It's basically a statement saying this is the energy. And thus they have concluded that dispute was simply due to insufficient care in specifying the meaning of the term force. So what possible explanation could you have for something other than force? What else would you call it? I mean, momentum is either energy, or vis-a-vis it is either energy. They both can't be energy. So how can you even possibly come up with any convoluted semantics to say that momentum is a real thing and we're just going to call it momentum and it doesn't mean anything? I mean, this is wave-particle duality. It is, when it's convenient, we'll use one formula. When it's convenient, we'll use the other formula. So whatever it is to our convenience, we'll pretend that's what it is. We'll entirely change the universe to suit what we're trying to accomplish. So the fundamental structure of the universe gets to change depending on whether we're making cupcakes or we're, making whatever, roast beef or something. The entire universe changes depending on what recipe we're trying to cook. Ovens change, temperatures change, pots boiling, everything change. All the physics change to suit whatever we're trying to show. So anyway, there's no, I can go on, but there's just no point. I mean, it's ludicrous to say this isn't a very important thing to nail down for physics. Insanely important. I mean, critical to getting the right answer is choosing well. You choose well here, then you have a chance of getting to the truth. You choose poorly, you have destroyed any hope of understanding the universe correctly, because you're getting hugely inaccurate numbers, a hugely inaccurate understanding of what's going to happen to the universe. Your rockets will land on the moon with one formula or the other. You can't use them both and both rockets land on the moon. This is the simple truth, right? There's absolutely zero doubt about it. This is the way you test it, right? So I've said that kind of thing. Well, let's go ahead and find a NASA engineer who actually has landed something on a planet and see if he used the kinetic energy formula. Because there's no hope that he did, frankly. Because it wouldn't work. He wouldn't get there in one piece. So it's clear that it could be settled, and it's not settled. It's clear that there are experiments you can do that will emphatically demonstrate one truth to be correct because it works. And it works in a big and complete way, where the other formula completely fails to get the right answer. It completely fails to land on the moon. Wait. All right, so I will attempt to elucidate some of the issue. So as I have attempted to point out, so we'll do the gravity thing first, because it might be easier to understand. I have asserted that you have to kind of understand that it is about time with gravity. So this is just an example to just point out that it's not about how far you go into the gravity. You don't measure something's energy by saying how high did it go. And you know it from your own experience. You know how much energy you would have to put into something. Like even if you had a little teeter-totter here and you were going to push it down and shoot something up fast, you know the heavier thing is going to go less high, and you know the light thing is going to go much, much higher. And you know it's not about how much energy you put in. The higher thing won't go higher because you put more energy and you hit it harder. It'll go higher because it's lighter. Okay, and it just doesn't have anything to do with how much energy you put in. So you know if I tell you that you used exactly the same force and you have an inverse relationship. This has a mass of 1 and a velocity of 2, and this has a a mass of 2 and a velocity of 1. And you didn't do more work. Come on. So right away, this is perfectly logical. The light thing goes higher. Now, why does it go higher? Well, the reason it goes higher is because gravity is rain. Okay, it is particles moving the speed of light. And you don't have to think of particles. I don't care. They're something that pushes on matter. Okay, that's moving the speed of light. We know this. Okay, these are facts we should be able to agree on, that there's something. Okay, and it's moving the speed of light. And it creates an imbalance between the surface of the Earth, producing less of it coming up, and there's more of it coming down. And that's gravity, 9.8, okay, amount of difference between the amount coming down and the amount going up. All right, and that anything put in that gravity, okay, is going to be moved down because it's going to get hit more from up there than down here. Now the key is this stuff's moving the speed of light. It's really, 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 really fast, this rain. So the rain is so fast that it really can't make any difference if you're here or here or here or here in terms of how much you're going to collect. It's coming down so fast that if you spend a little bit of time going from here to here, it won't matter. You're not going to collect any more of the stuff by moving into it. It's moving so much faster than you are, it would just be a tiniest of little shreds of extra rain you could collect. So it's hard to create an analogy to this because gravity's sort of unique. I mean, these forces are in the universe, and it's not like they create a whole bunch of copies of themselves. This isn't some kind of fractal principle that shows up all over the place. But the simple truth, because you can't really make a mechanical circumstance where I make a comparable physical force for you to interact with. I can't give you the rain analogy because rain's coming down so damn slow, right? I mean, compared to the speed of light. So it's like I can't create an analogy where you understand that you moving 1 mile an hour into something that's moving 1,000,000 miles an hour, you have no hope of collecting more of it by moving into it. It just, because all of this stuff here, ahead of you here, was all going to hit you anyway. Even if you stayed here, all that stuff was going to hit you anyway. Okay? And so you moving into it just isn't going to change anything. Well, anyway. So, the simple argument would be, is that you collect it. So I've said it's like mass is a bucket. So the bigger your mass, the bigger your bucket. So the longer you're in it, the more you collect with your mass. And the shorter time you're in it, and the faster you're going into it, the less you collect in your bucket. So it's just about how long you're in it. And the fact is this time is the same as this time. Okay, they're the same amount of time. So it's just about how much time you're in it, that you have time to collect it. And that's all that really matters, is time. Time. I think I said, no, I didn't say that quite right. It's not the same amount of time. It's the time is all that's going to matter about how much. So the smaller bucket needs more time to collect the force. So it takes it a longer time. So it travels a longer distance because it has to, let's say you gave it 18 worth of energies. Okay, so you gave both objects 18 worth of energies. The heavy object collects the 18 in less time, much less time. And the smaller bucket, the smaller mass, is collecting much slower, and therefore it takes longer for it to collect it, so it goes much further. All right, well, that's one way of saying it. So the other argument is you could use the argument of velocity in a direction. So I guess I'll throw that in just as another way of understanding it. You can sort of understand if you're moving very quickly through gravity, that you're not going to be able to collect, like if there was so much gravity falling in here, you're obviously going to collect less of it, right? So you can sort of get the idea. The faster you go, the less chance these raindrops actually hit you, And so there's less chance of you being affected by the gravity because you're moving so quickly through it. Yeah. All right. So I'll take a pause and we'll switch to the bigger picture subject and such. All right, back. All right, so I use a bowler as an example, and so we'll stick with the pins analogy and all that kind of stuff and get to the real heart of the physics. So I give you a simple argument. Okay, you can have an 8-pound or a 16-pound bowling ball, right? That would be the range that I think pros are allowed to use, or 10 to 16. They can choose what size they want to use. And none of the ones who win ever use anything other than the maximum weight ball, the 16-pound ball. Not that I ever heard of anyway. So the theory would be is, by momentum they have exactly the same energy. You can throw the 8-pound ball twice as fast as you can throw the 16. So the velocities, again, it's going to be velocity of 2, mass of 1. You could argue, well, let's just use the same number. So the 8-pound ball you give the 16 velocity to, and the 16 you give the 8 velocity to. So it's the same. But momentum says these two things are equal, same amount of energy. The kinetic energy formula, 1/2 mv squared, says the truth is this one has twice as much energy. So if you said the momentum was 100 watts or 100 joules or 100 pounds of force, their answer would be no, this 8-pounder has 200. Okay, joules, watts, pounds, whatever. Now, obviously, if it had twice as much energy, everybody would be using it. Twice as much energy would mean twice as much capacity to knock down pins. And obviously, they're not using it. And so it's kind of demonstrating to you that it can't possibly, 200, twice as much energy. Twice as much energy as throwing this heavy thing. Why would they keep throwing the heavy thing when they can throw the light thing and cause twice as many pins to fall down? Twice as much capacity to knock a pin down. That's what energy is. All right, so continuing with this analogy, let's imagine instead of just the arrangement of bowling pins, let's elaborate on the theme a little bit, and understand that the reality is so I could mark these. Well, maybe I'll put a little mark inside of these so you can make sure you see the difference. All right, so we'll just use that many. Is that the right number? I guess that's 10 pins. Yeah, why not? All right, so but the reality is in the universe, though, is that there's a bunch of other pins. Okay, there's pins everywhere. There's pins over here. There's pins. And as I've pointed out, if I hit the ball into a pin here before I even get to the pins I want to hit, let's just do this. These are the ones I want to move. Say I want to fill a battery, or that's the spring I want to compress, or that's the clay I want to, that's the place I want to measure my energy with. The truth is, if I put a pin here and I hit it, with the ball, before I get to these pins, I'm going to have less momentum. I'm going to have used some of my energy. So whether it's kinetic energy or whether it's momentum, I don't think anybody can logically say I can hit this pin, knock it way over here, all right, and that means I haven't reduced this 100 to maybe 98. Okay, so now I only have 98 going into the rest. And now I could make an argument to you, like a bowling alley has a wall here and a wall here, so these pins can bounce off the wall and back in, and so that's definitely to your advantage in knocking pins down, because you get to use the energy more than once. But you can sort of get the idea. The idea is you're going to hit a pin, and that's going to hit into another pin, and it's going to hit another pin, and that's going to hit another pin, and the energy is going to die slowly but surely. Each pin hits, and the next reaction is a little bit deader than the one before. That each time you hit a pin, you have 7% of the 100, and then now there's only 6% that gets here, and then there's only 5% that gets here. You're losing some of the energy with each interaction. You've consumed some of it in moving the pin, and so that would be the idea, to understand that that's what friction is. You're just transferred, instead of transferring the energy just to this, your spring or whatever you're trying to transfer it to, you ended up transferring it to a bunch of other stuff, right? So it went here, and it went over here, and it went all the kind of places, but you hit this one, it shot over here, and this one shot over there. So instead of knocking each other down, okay, they're knocking other stuff down. And that's where you lose your energy to heat or something. But the idea is if you create an arrangement of pins, where they're all in this box instead, then maybe you can hit that, and you'll have very little of the energy will escape, and you will just keep knocking pins in this way. And then you could just measure how much distance, and that's sort of what a spring is doing for you. It's creating an isolation, a separation from any other pins, right? The spring's not connected to anything. It's in the atmosphere, but very little of its energy will be leaked into the atmosphere. Now, you will create a little bit of a heat, so that means that the spring has some structure where pieces of the spring will be ejected. Okay, little shards of pin, so little pieces of the pins will fly off, and you'll lose some to heat. But generally speaking, you just knock down the pins. Okay, and it allows you to see how much energy you have, because it shows you how deep you go, is essentially telling you, well, how many pins did I successfully wipe out. All right. And so you can just understand there's different tools for measuring. Some tools are very good, some tools aren't so good. And you could obviously say with clay, you could understand that, oh yes, I'm going to lose lots of pins to, the environment. I'm going to move clay this way. and I'm going to move clay that way, and I'm going to be moving clay in a lot of directions that aren't the direction I'm trying to measure. So I'm not going to go as far here because I move stuff here and I move stuff over here. So I can't possibly get the distance I want because I move stuff. And the trick is the clay is basically saying the faster you go, like karate, breaking the boards, the more efficiently you break the board, the less energy it takes. The faster you do it, the faster your impulse, the more likely it is the board is going to snap. And by snapping, it saves you a lot of work. So it's like you trying to break a glass. Until the glass shatters, it's really hard. Once the glass shatters, it's really easy to, touch your fingers together. But until it snaps, you have to expend an awful lot of energy and get nothing in return. So it's just about eggs. You could say an egg. It's just about enough pressure, and all of a sudden you win completely. And now it really is easy. And that's all it's about, is snapping things, breaking things, cutting things. So you could argue it's just the sharpness of the knife. Velocity just sharpens your knife. So the faster you're going, the sharper your knife is, and the much easier it is to cut the bread. Okay, because your knife is so sharp. And the slower you're going, the rounder your knife is, and the more likely it is you're going to shoot stuff this way and this way and this way and this way. So it's sort of, again, like the sound argument, okay, that the faster the motion into the sound, into the medium, the more of the energy goes forward than goes in these other directions. So the faster you can move it, the more efficient it transfers it in the direction you want to go. And so the less you're losing to the environment. So the fast things don't cause as much of this, okay, this stuff on the sides, because the motion is quick enough to snap all those connections. So to make it more relevant to the real physics of the electrodynamics, I will attempt to do that by just explaining briefly that you could argue that just like gravity, okay, in a sense, the atoms are attached to each other by connections, discrete connections. This one has a positive nucleus and this one has a positive nucleus, and they have negative stuff on the outside. And the negative thing can just have a loose connection. See, there's an electron here, an electron here, and this one has an electron here, and he could just sit there and say, I feel this one's proton, and so I'll hang out here because it's enough. And that's what's connecting atoms to each other. They're not connected by hard bonds like real chemical bonds. Like it's not like a water molecule. It's just the water molecule sticking to each other. Okay, so there's different kinds of bonds. And what you're basically saying is what I'm basically saying is the faster I can separate them, the less energy it will require. So because it's just kind of like gravity. The faster I move these charges away from each other, the less chance the charge has to react. So it's they're basically, their attraction is made out of pushings. Okay, everything's pushed together, not. Let's see how to explain that. So everything's feeling forces. Okay, and what you're basically saying is you're going to try to move these two things apart so quickly that the force doesn't know you did it. Okay, essentially. And so you're going to pull them apart before these forces that are coming from the outside that are really pushing them together have a chance to know that you moved this one over here. So if you can get it out of this force quickly enough, all right, and you have a chance to do that in this circumstance, right, because these are tiny little things in the force. So a tiny distance means you evaded this force. Just all you have to do is move a tiny distance and you've evaded force. So it's real plausible and doable to move things out of the force quickly. But if you move them out slowly, the fact is the force will compensate for the fact that you're moving them out of the pressure, and it will react by these other influences having time to tell it you can't go there. The other electrons will have time to tell this electron you can't go there. It'll fight back, essentially. So that you can understand that on this tiny molecular level is different than the big rockets flying around the Earth level. and that you can defeat the force on this micro level, and you can't really defeat it on the macro level. All right, what else to say? So yeah, so I think the analogy of a sharper knife works. I mean, I hate to turn it into a physical metaphor, but it's just sharpening your arrow, making it more aerodynamic, and that's what velocity does for you. It makes it possible so that when you hit into atoms, you break them, you snap them like a karate guy. Okay, you snap the boards, and by snapping the boards, by breaking them quickly, you actually use less energy to break the board. Where if you apply the pressure slowly, okay, not what's that kung fu guy's name? Anyway, the 1-inch punch kind of thing. Yeah, so if you do it slowly, you'll apply a lot more force, and you might not even break the board. You'll end up just creating heat and a lot of other crap. So clearly, slow things have a huge disadvantage in going through a substance, because they're not going to snap the boards. They're going to keep smashing their fist against the wall. Ow, ow. They're never going to go in quick enough to snap anything. And so it's all going to be a lot of hard bending and breaking. They're going to have to bend it first and then break it. No snapping. So it's basically just saying it's a dull knife. The faster you go, your knife looks like this, and the faster you go, the more your knife looks like that. So it's just a matter of how well you can plow through material objects. And that's all that the going further means. It doesn't mean you had more energy. It means you interacted with the universe less because of your velocity. You didn't have to split as many atoms. You split a lot fewer right here on this surface. This is the only ones you affected on the board. By doing it quickly, that's all you affected. Is the atoms right here. It never reached anywhere else. The energy you didn't waste it on a whole bunch of other places. You just did 10 atoms worth of damage, where if you go slow, it's going to take you 35 atoms. And so we're back to the speed argument, speed versus distance. So again, this is an argument that in all the cases where you see the lighter thing create more damage, it's not really creating more damage. It's the same like you can make the argument the fast bullet and the slow bullet going into a brain. They're both the time they're in is the time they're moving is the part that's significant, and so it's about time, not distance. And time just means how much stuff are you hitting. Okay, how much stuff are you interacting with? So going slower means you're going to interact with more stuff per inch than if you go fast. You're interacting with a lot less stuff per inch. All right, it should be understandable. Let me fix my 8-pound ball. So I'm just saying we probably can find analogies. I mean, I can't use baseball as an example just because obviously baseball has to do with how much you're connected to the bat. I mean, obviously the baseball player would like to use a lighter bat, get a higher bat speed, but then the problem is his wrists have to be super, super unnaturally strong, because the bat itself won't have any momentum when it hits the ball, the no mass. And without the mass, okay, the bat's going to have that opposite reaction thing's going to happen. There's going to be a huge jolt in the opposite direction before his body's momentum can actually push through. And the other thing is you're just going to break the bat. So it's not a good example just because, like golf, the club head isn't freely flying. It's connected to the shaft and it's connected to your whole body. So its mass isn't its natural mass. It's a connected mass. And so the dynamics are a little different. But the argument could be made, right, is that, technically all you want is the speed. If this was true, But we know that it's not just about speed. That you have to be able to impose to impose energy, you also need enough mass, okay, to carry your energy, the momentum. And that But clearly there's every example that in sports there's no example of this rule working. That all you have to do is go faster and you've created many times more, much more energy than you would create if you went with the heavier thing. So there's just no evidence that lighter produces more effect, more energy. All right. I think that's probably a good enough argument for that phase of this. Now I guess I'll just make some concluding remarks and see if I can come up with any other examples. But, I mean, that's all it's really about. It's about how science measures things. And I'm just saying there's absolutely no way that any of you, if you have any mechanics knowledge, could see any way to defend the kinetic energy formula. It's just indefensible rubbish. It just can't be defended. That this is the simple explanation for why fast things go further is because they do affect fewer molecules, and the slower thing affects more. There's more interactions taking place in its environment. There's more time for the forces to interact with it. And if they're going fast, there's less time, just like going through gravity. The faster I go across the gravity, the less of the gravity pushes on me, and that's why it's less effective at bending me towards the earth, is because the faster I go, the more I undo its effect. I mean, it's... Well, anyway, it really you should be able to understand. You really should be able to. All right, so in closing, I would argue that none of this history, none of these facts regarding this controversy, the fact that why are there these two weirdly different formulas essentially describing a similar thing, or in overtly the same thing, but it's not taught as the same thing. Clearly, no physics lectures I've ever seen even mention the existence of a controversy. None of them even talk about the two things in parallel as if they are opposing viewpoints of how the universe functions. None of that is talked about, and so most, I guess, physics students just don't realize that it doesn't make any sense that they have these two different answers to the same question. And somehow, I guess, they have to figure out where they let go of one and go with the other. As pointed out, you're not going to be a very good bowler using the kinetic energy formula, and you're not going to be a very good lander on Mars if you're using the kinetic energy formula. Just a fact. So clearly they have to have enough knowledge to know when to apply them. Now, I don't know in what circumstance ever the kinetic energy formula ever, like in the one case, it's only one case where it gets the right answer. Okay, when the mass and the velocity are the same, and you don't change anything in its adventures in the universe. But the fact is, the numbers are very wrong, and so I don't know in what case they actually have some benefit by getting the wrong answer. And I would argue that clearly all of the nuclear quantum mechanics kind of physics that depends on them understanding how much energy an electron has, all of that is based on this insanely exaggerated numbers. So everything they understand to be related to each other in some way, or measuring, how much energy is in the sun, they can't be getting anything like a right answer using this formula. And that might be why we have inventions like neutrinos, because they can't account for where all the extra energy went. They can't just say, well, it's heat. Oh, that's right, the sun's already hot. Yeah, I already accounted for the heat. They won't have an excuse to say it. They can't say silly things like, well, 99% of the energy disappeared as heat, without proving that. So, it's just strange that physicists can know of these two different ways of looking at the universe and not recognize that there's something overtly wrong in these two different definitions of something so fundamental. And again, all of the semantics they use to cover up the fact that this was a controversy. See, I mean, back in the 1700s, they didn't play games like, well, kinetic energy is a scalar, you see, and the other one is a flattened matrix. And so, or some kind of, there's no bullshit to cover it up. I mean, they were clearly competing, and there wasn't any words that they could just hide that through by saying somehow kinetic energy doesn't have a direction when clearly every one of the experiments has direction. And that somehow momentum has something called negative momentum, when of course it doesn't. That's completely arbitrary. And based on relativity, which they all sort of believed in, why wouldn't you already understand? See, they understood in the 1700s that, we don't know exactly which one has the energy. Whether the brick wall is moving into the bullet or the bullet's moving into the brick, we don't know for sure exactly which one's carrying how much of the momentum vectors. And it doesn't really matter, because all that does matter is the difference in the vectors. So anyway, but this whole idea that somehow energy isn't a vector, just, I don't even know how they fall for that. What do you mean? It doesn't. What do you mean? It's exactly the same as the momentum. I mean, there's no difference. It's clearly linear. You know, it clearly has components in the three dimensions. I mean, even if you're doing a more complex problem, with multiple objects moving in different directions, they know that it's the same thing. Figuring out which way the momentum's going is going to be just the same thing as figuring out which way the energy's going. So, there's just so much, it's just, frankly, bullshit, baked into this hundreds of years of becoming comfortable with an insane idea that somehow there's compatibility between these two different definitions of a fundamental entity, something just force, something this fundamental, and they have two different definitions of it. It just doesn't make any sense, and I don't know why. I mean, this is sort of proof that it is a religion. Okay, this is just religion. It's just dogma. This controversy needed to be settled, and they just made it go away. Well, there's this whole period of physics, you have to concede, that was pretty not very interesting. Except for Maxwell, I suppose. The 1800s, there just wasn't any really good physics. And, there wasn't anything that just stood out as, wow, they answered a lot of questions in that period. And then the Industrial Revolution happened, and all the physicists sort of became inventors. And so it wasn't about the physics. It wasn't about understanding elemental physics anymore. It was just about inventing things. So that made a difference too, I suppose, to the physics. But anyway, whatever. I mean, anybody can paraphrase it any way they want, then reductionism, and figure out what the key things are. But I'm just saying, this is a completely, you have a huge controversy for very good reason. Very, very Leibniz's view of how the universe, stuff moves in the universe, completely different than Newton's. Completely different universes. Again, if you use the two formulas, you will not navigate the universe the same way. And it's just a fact. And we know that it's critical that you have all the right numbers, or you're not going to be able to land on Mars. So to say that they don't have the answer to this question, they must have the answer to this question, and they just don't feel like answering it. They don't feel like saying, yeah, of course, when your life depends on it, you better use the momentum formula or you're going to die. Because that's the real one. That's the one that is real physics, and the kinetic energy formula was just a mistake. It was just a nonsense road traveled because of really poor physics. That is, seems like physics. Well, it seems like it must have more energy if it went higher in gravity. But then you just think about it for a minute and you can say, well, it doesn't matter, because I know it's easier to throw lighter things. I use less energy, so I can't possibly say there's more energy in the lighter thing because it was so much easier to throw in the air. It doesn't make any sense. How can it have more energy when I put less energy into it? That can't make any sense to anybody. That's the implication of that formula. Just understand. The formula is basically a free energy formula. It basically says the lighter the thing you throw, the lighter the thing you eject with your energy. Okay, with the amount of force you can apply. You're wound up. You have wound up your God, I can't think of any of the words. that thing that catapult. You've wound it up. You know how much energy it has. It always, you know exactly how far it throws a cow. Okay, and they're basically just telling you if you throw lighter objects, you'll make more impact. You'll have more energy. You'll gain energy just by putting lighter things on the catapult. And it's just overtly silly to think so. All right. So I've said I can only, I'm doing my job. I'm attempting to reason with you. Now there's lots of subjects in physics I'm arguing are wrong, and this is just one example of how wrongness just slips, under the radar. That physics's bad science radar is really bad, really, really bad, and that a lot has gotten by. A lot of junk physics has gotten through the filter. Their filter for pseudoscience isn't very good. And that's why you have wave-particle duality. That's why you have a theory of gravity and a theory of quantum mechanics that are completely incompatible. That's why it is this monster, this Frankenstein monster, is because it really wasn't a very disciplined experiment, this evolving our knowledge. They did it in a shabby, sloppy way. And instead of getting right answers, they settled for unanswers. Just basically stuff so mushy that you can only call it religion because it's not an answer to the question. Yeah. So, just saying, it's all kind of bad on you people that you don't understand that this really is a question that should be answered, and that there are still overt reasons to address the facts. Okay, the facts that can be presented showing how this kinetic energy formula can't possibly be true, that it does in fact create fake, exaggerated notions of energy, like free energy. I mean, it's not free energy because you can never collect it, as I pointed out. So it's clearly not free energy. It's just fake energy. So come on. Save science. Quit defending stuff that's just junk. It's junk science, and it's right there in the middle of your physics. It's it's a cancer tumor in your physics theory. This physics isn't going to survive and thrive with these huge glaring wrong answers in the elemental structure. It's going to have to seek treatment eventually. So why wait till it metastasizes? And I'll give you another analogy. I mean, that's just kind of a creepy one, but I mean, it's really these are fatal flaws. These are things that will have to be addressed because this physics monster will not survive because its leg is tied to its ear. I mean, it's a monster. All right, that's probably a good enough analogy. All right, I'll go with that one. So, I think I'll link in the description to this very interesting read, sort of, kind of, history and stuff, and blah, 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 blah. But it's way longer than it should be. And, what can I say? That's all. It just doesn't advance it much. Like I said, all you find out is that there was just the two sides. The side that understood that. See, it's really just about. They really weren't. They were trying to say that all these forces were the same. When I've tried to say you can't compare two big pool balls hitting each other, and what gravity's doing. The forces moving things, on the subatomic level are different than the forces being transferred between cue balls. I mean, the elemental force, I'm saying, yes, of course it's the same. But the way the force is interacting is so different. We can't turn gravity into a laser beam. We can't do things to gravity that you can do to the electrodynamics that are conveying the force inside of two pool balls. So let's see how to. Yeah. Well, anyway, and yeah, the fact that there wasn't enough recognition that you really can't. Springs are different than magnets, are different than clay, are different than blocks of wood, are different than rocks on a road, different than sand. All these things are different in how they're going to react to momentum or the movement of an object through them. And you can't just do this what does it look like thing, because it's not going to give you the right answer. Seems like isn't necessarily is like. That's a really important thing that just science, physics just couldn't care less about that cautionary statement. That's the one they stepped over a lot to get where they are. All right, that's probably enough. All right, so like I said, if somebody has some evidence of the kinetic energy formula applied to bowling balls, applied to anything where without the kinetic energy formula nothing would make sense, I'd love to see it. Because I'm quite certain it always gets, if you use it, you're using the wrong answer. And maybe the wrong answer will be useful in some way, but it won't be telling you the truth. And the real truth will be visible. Because all you have to do is the experiment with a spring. You just do the experiment with some other device for collecting the energy, and you'll see that you had the wrong answer. All right, enough. So, till the next time, and such.